This is problem 2 of the Ops Research Final by Justin Nathanson. So here we are given the problem where it is a maximization problem with 3 decision variables, x1, x2, and x3, all subject to 2 different constraints. So for part A of this problem, we're given the optimal solution and the final set of equations that represent this optimal solution. And at first it's hard to interpret. However, we decided to put it in tableau form to be able to easily interpret the results. And then we found that x1 is equal to 5/3, x3 is equal to 3, and this gives us a z value of 17. Then we were asked to construct the dual of the problem, which is extremely easy, and it just involves transposing pretty much everything. And since the primal problem has 3 decision variables and subject to 2 constraints, we know that the dual problem will have 2 decision variables, y1 and y2, subject to the 3 given constraints. And what's important and what's useful about the dual in this situation is it's a lot easier to plot, and it's a lot easier to determine an optimal solution graphically. And this can be seen as we, in fact, have done this, and we solved for the optimal solution, which we found 3 feasible corner point solutions, and we found that point 2 where y1 is equal to 0.2 and y2 is equal to 0.6 gave us a w value of 17, and as we know, when w is equal to z, this is an optimal solution. So now for part D, we see that the coefficients of x2 in both the cost function or maximization z function as well as the 2 constraints has been changed. And so now we need to determine if the previous optimal solution is still optimal. And as we did in the previous parts, we used the dual of the problem to solve this problem because it's much easier to visualize these things in the dual, which can be seen to the right in a graph where we see that the previous optimal point solution is no longer in the new feasible region. Therefore, we can automatically claim that the previous optimal solution is no longer the feasible optimal solution. And so now for part E, we have to determine what the new coefficients of x2 are in the final set of solution equations. And to do this, it's actually pretty easy. We multiply a matrix containing the original slack variables by the new set of coefficients of x2 in the constraints, and we get that the new coefficients of x2 in the final problem will be negative 1/3 and 4/5. For part F, now we go back to the original given problem as in part A, except we add a new decision variable x2, x new, to both the z function and the 2 constraints, and now we need to determine if the previous optimal point solution is still optimal. Again, we use the dual because it's easier to visualize, and as was before, we see that the previous optimal point solution is no longer in the feasible region. And we found that the new feasible solution is at y1 equals 0.4 and y2 equals 0.4, giving us a w value of 18. Moving on from this, we were asked to confirm our answer and determine what x3 and x new would be in the in the primal of this problem using the complementary slackness value. And in order to do this, we had to convert the dual problem into its canonical form, which means that we had to include surplus variables s1 through s4. And from this, we found that s1 and s2 were both non-zero values, while s3 and s4 are 0 values. And due to the complementary slackness theorem, we know that since the surplus variables s1 and s2 in the dual are non-zero, we know that the decision variables x1 and x2 in the primal are both 0, while the opposite is true for x3 and x new. And through basic manipulation and algebraic rearrangements, we found that we were able to solve that x3 is equal to 2 and x new is equal to 5 in the primal problem. And then finally, we were asked to determine what the coefficients of x new would be in the final set of solutions or equations. And as we've done in part F, it involves multiplying the slack submatrix by the coefficients of x new in the 2 constraints that were given, and we determined that the coefficients of this variable would be 1/3 and 1/5 in the final set of solutions. Thanks. Fucking class sucks.